See. Good morning, students. Good morning, everyone. I believe you are all doing very well. Good morning. I want to be sure you are hearing me. You can just respond if you are hearing me. Good morning. Please, can I see your reaction if you are hearing me? I want your reaction if you are hearing me. Good morning. Okay, thank you. So there is one that I put my name. Okay, good morning once again. I believe you are all hearing me. You are welcome back to CHM 101 class. I'm sure you had a very good time with the past lecturers, especially the immediate past lecturer, Professor Woyomi. And I am Professor Grace Ogunlusi. I will be teaching you thermochemistry. I'm going to be teaching you thermochemistry, so let's get started. First, we need to remind ourselves what thermochemistry is. Thermo, from the name, implies heat. So we are talking about the study of heat changes that are associated with chemical processes, either at constant volume or at constant pressure. So for every chemical process that involve change of states, most times you are going to find that there is going to be heat exchange or heat changes. So the chemical processes generally involve heat, whether it's at constant volume or at constant pressure. And the study of that change is what we refer to as thermochemistry. So quickly, I have the outline here to show you what we should expect in this course. What we should expect in this course, we are going to have discussions around subtopics like balancing of intermolecular forces, hydrogen bonding. I know you are familiar with many of these topics, but we will take them a bit deeper than what you knew at O level. And then we will talk about other disorder phenomenon. We'll discuss entropy, free energy, and energy effects. Then we move on to thermodynamic, exothermic and endothermic changes. I know many of these terms are not new to you, but we delve deeper. We will consider enthalpy law of reaction, Hess's law of enthalpy summation, which will also involve discussing relevant calculations. We will be discussing heat of neutralization. We will also look at combination and formation. We will discuss bond dissociation energy and look at relevant examples. Then we will look at free energy and spontaneous change. So that is how much you expect in this course. So let's start with intermolecular forces. Let's discuss intermolecular forces. What are intermolecular forces? You are very much familiar with bond formation. And in bond formation, we talk about sharing of electrons between two atoms or more atoms to form a molecule. And in the case of transferring electron or sharing electron between atoms or among atoms, you form what we refer to as chemical bond. That kind of interaction is an intramolecular interaction. And so intermolecular is different. I started from what you are very familiar with to what you are not used to. So intermolecular means that when you have molecules that are already formed as a result of the existence of the chemical bond, which is an intramolecular force between them, you have molecules coming together, and in their coming together, they have some kind of forces that hold them together. And those forces are what we refer to as intermolecular forces. So you recall that all atoms can form stable units called molecules by sharing or transferring electrons. And that is what we refer to as intramolecular bonding or intramolecular forces. That means within the molecule, those are forces that keep the molecule together, and that is well known to you. So intermolecular forces are those forces that exist between molecules or particles. They can be between ions, they can be between atoms, and they are that is between molecules rather than within. So they are just holding the molecules together. For example, one molecule that you are very familiar with is H2O. Between hydrogen and oxygen, you have bond formation. That is a kind of bond that is referred to as intramolecular bond or intramolecular forces. But one molecule of water coming closely with another molecule of water, we form large amounts of water. So that is how you form your particles. And so, you form the large molecules because there is a force that holds individual molecules together. And those are the intermolecular forces we are referring to. We also mentioned, we can put them in short form as IMFs. And generally, they are non-covalent attractive forces between atoms, molecules, and or ions. So they hold the molecules together in a substance, and they determine many of the physical properties of a substance. So the stronger the intermolecular force between the molecules of a substance, you find out that the better the property, especially the physical property, is defined. So if that force is very strong, you may find out that the boiling point will be very high, or you may find out that even the amount of heat that is required to break it down, when we get to that, we will see all of this play out. So they play a very significant role in determining the physical properties of substances. For example, you look at water. We know that water can change from solid to liquid, and it can change from liquid to gas. So you can go from solid to liquid and to gas. And the molecules will remain intact. I hope you understand. Water will still be water, but it can exist as a solid, as liquid, or as gas. But this change of state will be due to the changes in the forces among the molecules rather than those within the molecules. That's why the H2O bond will remain, whether water is in gaseous state, or is in solid state, or is in liquid state. But we can see the states will be defined by how strong the bond, the forces holding the molecules in that substance together will continue to hold. So if you have a solid state, you know that that force that is holding all the molecules in water together must be very strong, and that is why they can exist in solid states. And if it is so loose, so weak, then you can see that they will be in gaseous state. That means more molecules can move randomly, but each molecule will still maintain the intermolecular bond. So that is very important for us to know. So let's talk about the strength of these attractive forces. You see, when we talk about the strength of the attractive forces, it varies. And usually, when you see small molecules, they exhibit small IMFs. And though usually the IMFs between small molecules are weak compared to the intramolecular that hold the atoms together within a molecule. So in essence, we are saying that if you compare the strength of the bond to the strength of the intramolecular forces, no matter how small the molecule is, the force that is holding the atoms together, as in the intramolecular forces, they are stronger than the forces that are holding the molecules together in the particle. So the strength will vary also depending on the size of the molecule or the nature of the attractive force that is between them. We will look at these different attractive forces, that is the IMFs, very shortly. So the bulk properties are also very important for us to note. They are a measure of how strong the attractive forces are between atoms or molecules. So the state of matter, essentially, like I said earlier on, depends on IMFs. Let's look at how these come about. What causes intermolecular forces? If you look at a molecule, like the example that I have here, so if you look at the example that I have here, I've shown you molecule A. This is molecule A and this is molecule B. Molecule A, we are taking it as neutral in this sense. So we are using examples. We are using examples of a neutral molecule like Cl2, chlorine. Chlorine molecule, you know, you cannot say that it's polar because you have similar atoms there. But when they come close, one molecule comes close to another molecule, there occurs some changes in the arrangement of the electrons. Don't forget that these electrons are all negatively charged. They are bound to repel one another. But in the course of trying to come close, there will be some rearrangements that leads about redistribution of the electrons such that they can accommodate each other. So you find that the electrons will be more dense at an area, like you have in molecule A. If you look at my finger, I'm putting a circle around here. You can see that the electrons around there, if you have to cut this into two, you find that the electrons around there are more. In this case, I've just used a case where the electrons are evenly distributed. So you see that as the electron in A repels the electron in B, there is that redistribution, uneven distribution, I should call it, of the electrons around molecule A, meaning that this part of the electron, of the molecule is densely populated with electrons, whereas this side is less dense. And that is what we refer to as instantaneous dipole. Instantaneous dipole. So as they approach each other, the part that is denser in electron will be assigned partial negative charge. So that is the partial negative charge on top here. So that means it is electron rich or denser than the other side. So we take, this is partial positive charge, meaning that the electron here is a bit depleted. So it's not a full charge. In full charge, we talk about transfer, complete transfer of electron. So what we have here is showing that we have polarized the molecule. So this is the side that is less dense, we carry a partial positive charge. The side that is denser, we carry a negative partial charge with negative sign. So this is what happens. And as you can see in this particular example that I gave here, instantaneous dipole has been formed here. So this is just what I've explained, where you have electrons orbiting within a neutral atom or molecule, and then as you go on, you find out that the electrons can become unevenly distributed as they approach each other, as one atom or one molecule is approaching the other. So we see the electron become unevenly distributed, leading to instantaneous dipole. So we call that instantaneous dipole. It's not a permanent dipole, because in permanent dipole is actually a type of bond that you have in molecules. So then if you look at what happens after the interaction has taken place in the example I started with, you can see that once they come so close together, the instantaneous dipole that is formed is shown here. So in this case, you now have molecule A that is partially charged on two sides. One side is partial negative charge, the other one is partial positive charge. And because of the close approach that it has to molecule B, B also becomes charged. But the one that is closer to the negative charge of the molecule A will now carry a positive charge for there to be that attraction. They must be oppositely charged. And then the other side is denser and it is negatively charged. So that is how electrons in B moves away from A and a dipole is formed, causing attraction between the molecule. I hope that is taken. So before I continue, I want to give you the code for attendance. I hope you are there with me. Let me share the code with you now. The code, first code, all in capital letters, is E. E for Esther. Y for yoga. C for total, Y for yoga again, and D for dog. EYCYD. EYCYD. All in capital letters, uppercase. EYCYD. EYCYD. Thank you. So I'm going to continue with the class. I hope you have, I don't know why you are posting it. We have told you again and again not to be sharing the code on the YouTube chats. I don't know why you keep sending that. I can see you, Temitope E9Y. I can see you, Tobi Akiyemi. Taufik Barakat. I don't know why you are sharing it. You heard me clearly. And even Emmanuel, a number of you sharing this code, it is unethical. You are not supposed to share the code on the charts. The code is strictly for those who are in the class. Thank you for retracting it. Rejoice, Yanolua. So I will continue my class now. So still talking about intermolecular phases, I've just used one clear example, very, very apt. If you look at hydrogen chloride, you have hydrogen and you have chlorine in that molecule. And hydrogen chloride, as it is, has an existing bond between the hydrogen atom and the chlorine atom. So as you can see here, this is the HCl molecule, and with another molecule in close proximity, we have HCl molecule. So let me quickly remind you, for every 1 mole of a substance, you will recall that you have 6.023 times 10 to the power 23 molecules in it. So when we say 1 mole of HCl, we mean that in that 1 mole, you have 6.023 times 10 to the power 23 molecules present. So how do those molecules stay together in 1 mole of a substance? That is what the intermolecular force does, holding all of the thousands of molecules together or millions of molecules together. So that is what it does. But each molecule has its own intramolecular force, which is the chemical bond. So for HCl, you have the chemical bond, and that is what I have marked there as intramolecular force and indicated as very strong, because chemical bonds are very strong. So that is what we have between hydrogen and chlorine atom in each molecule of HCl. So coming in proximity with another molecule, there has to be that attraction to hold them together, and that is what the intermolecular force does. It's a weak force, but it holds all the different single molecules together. So when you say HCl, 1 mole of HCl, then you can just imagine how all of those molecules are held together in the gaseous state that you can have hydrogen chloride. So partial charges are indicated here for you to be able to comprehend all that I've been saying. Now, I must mention that in HCl, for instance, there is permanent dipoles. What do we mean by this? Because of the difference between the hydrogen atom and the chlorine atoms in terms of electronegativity, they have permanent dipoles on them. So when we talk about those permanent dipoles, they also play a role in the nature of the intermolecular force. You will soon see that as I continue. So there is this permanent dipole. In this case, they have permanent dipoles. So the kind of interaction that hold them together is what we refer to as dipole-dipole interaction, because they hold permanent dipoles, and so their dipole, the dipole from one and the dipole from the other, can interact. So you will see as I go on with more examples. But this is a case of a polar compound or a polar molecule coming in close proximity with another polar molecule, having permanent dipoles. So this also determines the kind of intermolecular force that occurs between them. So without wasting much time, there's something we need to address. How do these molecules balance to attain a particular state? How do you get the molecules to occur when they come in close proximity now? How do they appear or occur as solid or as liquid or as gas? There are 2 main factors, and we refer to this as balancing of intermolecular forces. Each molecule that has a chemical bond has a lot of energy in it. And this energy also contributes to the motion of the molecule. So if I have HCl that I just finished using as an example, because of that bond, the bond is loaded with a lot of energy. The molecule has kinetic energy, naturally. Even any atom has kinetic energy. You know about kinetic energy. So we have to consider the kinetic energy of the molecule. And don't forget, this also varies. So atoms, molecules, or ions that make up the substance, they possess kinetic energy. And this means that the molecule can continue to move apart. They agitate, they are in motion. So their moving apart can as well affect their staying together with other molecules. How do we balance this? The second factor we need to consider is the fact that the attractive force that hold the particles together, they also play their role, which means that the intermolecular forces, they serve as attractive forces between the particles, while the kinetic energy has the potential to keep them apart, keep the molecules far apart. The attractive intermolecular forces bring them close together. So between them being far apart, separated due to the kinetic energy when it is very high, and it prevails, something will happen to the state. When it is low, and then the intermolecular forces are a bit stronger, then a different state will emerge. So there is that need to balance between these two factors, and that is what determines the phase of a substance. So the preferred phase of the substance will depend on the strength of either of these two, or the strength of both, rather, because it will depend on the strength of the kinetic energy. If the kinetic energy is so high, so large, that means Ke is greater than attractive forces. And by that, you're going to have a gas phase that will be prevalent. If the kinetic energy is lesser than the attractive forces in terms of impact, then you can have a liquid or you have a solid. So kinetic energy being greater than attractive force will lead to a gas phase. And if you have the kinetic energy that is less, that means the molecules are not in so high motions that the attractive force can hold them closely or tightly together. Then you can have a liquid state or have a solid state formed. But there's still one thing we must not overlook, and that is the role of temperature in balancing intermolecular forces. So when you look at the kinetic energy and then you look at the intramolecular forces, to know the preferred state, you must not forget to talk about temperature, because as we increase the temperature of any system or molecule or particle, what you are doing is that you are supplying kinetic energy. And as you supply that energy, whether you supply it in form of heat, of course, it is used as kinetic energy to increase the motion of the particle. So as you can see here, in this diagram I've shown you, increase in temperature, we change the state from solid to liquid and then to gas. So if you have gas, what can you see in this diagram? You can see that the space or the gaps between each particle, each molecule is so large because they need space to move around at such a high kinetic energy. Whereas in liquid, it's somehow moderate. They are not tightly packed, but they are not so loose together. They can still flow together. That is why you see liquid will flow together, and you see that crystalline solid will just stay together as a substance, staying together without flowing. Whereas for gases, they can be in a large space because the kinetic energy is very high. And then what happens is that if you have high IMF or very strong IMF, if it is possible to increase the intermolecular force, or if, let's say that if you have a kind of intermolecular force that is weak, then you will have gases. Because the weak forces, we still allow the molecules to move as far apart as possible. If the IMF is high or stronger than what you have in a gas, then you will have liquid. That means they are held together, they can move together. So let's go back to the example of water that you are all familiar with. If you can reduce the temperature so low to say -4, -5, -13, you will have a solid substance formed because the IMF has been increased as you lower the temperature. But if you leave it at room temperature, you're going to have it in solid form. You can put it on the table. You can see the water flow together. You can see drops of water. You can see running tap. Molecules are still going together. You can't run ice through the tap. They cannot flow together. So the tap, in fact, the tap will be clogged because that solid will just clog the outlets. So, but as liquid, at reasonable temperature between 0 and 100 degrees Celsius, you will still have it as liquid. But as you increase the temperature higher, you supply kinetic energy. The molecules can bubble, escape as vapor, be all over a big space, a big room, a big container, and that is what we are describing. That increasing the IMF will also bring about the change in the state of the molecule. If you increase the IMF, it can move from gas to liquid and then to crystalline solid. So transition between solid, liquid, and gaseous state of a substance occur when conditions of temperature or pressure, that is another factor we can mention too. Temperature or pressure, if it favors the associated changes in intermolecular forces. So that is very crucial. And I put a footnote here that the space between the particles in the gas phase is much greater than what is shown. I'm sure you quite agree with that. So those two factors, temperature and pressure, they also play a significant role in determining the kinetic energy of the substance, and also in determining the states in which a substance will exist. So still talking about balancing of intermolecular forces, I've just summarized everything that I've said so far here, that at low temperatures, you're going to have most substances as solid, except for helium. Helium is known to be a liquid at absolute zero. Absolute zero means minus 273.15 centigrade. So absolute zero is 0 Kelvin. Then, as temperature increases, substances with very weak intermolecular forces become gases directly. That is also very important for you to know. So it is possible for a substance, as you supply kinetic energy in form of heat or increase in temperature, the substance can go from solid to liquid, like you have in the case of ammonium chloride. It sublimes straight away. You don't even form this liquid. All you get is a gas as you heat it up. Substances with weak interaction can become liquids as temperature increases. So generally, we are saying that increase in temperature increases the kinetic energy of the molecule. And as the temperature increases, all substances, no matter how strong it is, we can go from solid to liquid and then to gas. Also, it is important to know that as bonds become more polarized, the charges on the atoms become greater, the intermolecular attractions become greater, leading to higher boiling points. So generally, you know that it will take a lot of kinetic energy to convert substances from very solid, solid states like crystalline states to liquid and then to gas. So this is very important, and it also depends on some other factors. So quickly, I'll talk about the types of intermolecular forces. I will lay that very strong foundation for us to understand what to expect. There are basically 4 types, but we discussed 5, and I'll tell you why we are discussing 5. So types of intermolecular forces, the first one is the dispersion forces. That is also called London dispersion. London dispersion is in all substances because instantaneous position of an electron in any molecule can make a point in the molecule to be negatively charged, like I've explained earlier on. And so the rest of the molecule will become positively charged. So in any substance at all, you find electron, you will find dispersion forces. So it's the only IMF that occurs between non-polar molecules. So for non-polar molecules that do not have permanent dipoles, like hydrogen, like CCl4, like CO2, and many others, you will find electrons. Because you find electrons, you will find dipole forces. So that's the weakest IMF. It's the weakest of all of them. So I've also described it here, where you come in close contact, like I said earlier on, you have the partial charges that are temporary dipoles. And that is how you form dispersion forces. So whatever force is holding them together is referred to as dispersion forces once they don't have permanent dipoles. And so you can see an example in iodine, I2. I2, as you know, is neutral. I mean, it's not polar. So you can see I2, when they come in close contact, you form instantaneous charges on them. They are partial charges, and so they can hold together. So if you look at how they affect the state, I put a table here that shows that dispersion forces increase with molecular weight. This is because the number of electrons will be more as the molecular weight increases. And the greater the number of electrons in the species, the stronger the dispersion forces. And that is why for halogens, you have fluorine, chlorine, bromine, molecular weight is displayed there. You can see the boiling point increases as we increase the number of electrons. So down the group of halogens, their molecules, their atomic molecules increases in boiling point, and also the melting point. And sometimes smaller molecules are gases. So if they are so small, it means that they are weak. The bond that is holding them together can be so weak, and then they can exist as gases. And larger molecules can be solids. And at the same temperature, considering all of them at the same temperature, you will find that the molar mass will determine their boiling point and their melting point and the state in which they exist. The second one is the dipole-induced dipole forces. I want you to just look at this name, because this is how I teach students. This thing is not difficult to understand. Dipole-induced dipole. From the name, it implies that one of them has a permanent dipole. The other one is non-polar. So the presence of the one that has permanent dipole coming in close contact with the one that has no polarity at all, that presence can polarize the other one, and the effect is called induced dipole. So there will be formation of an induced dipole, which is a temporary dipole. So combination of these two will give you the kind of force that is easy to just understand. Dipole-induced dipole forces. So these are forces that occur between molecules with permanent dipoles and those with polarizable electron cloud. And I've put an example here. If you look at hydrogen chloride is polar. I explained that earlier. But argon, you know it as an inert gas. So argon does not have any dipole, any permanent dipole. But in the presence of HCl, the electrons in argon can be polarized to carry those partial charges, which are temporary dipoles. And so those are the ones we refer to as induced dipoles. And you can see the arrows here pointing to the fact that as they come close, they induce charges on argon. So the chlorine, you know, is more electronegative, so it's going to carry the permanent dipole with negative charge, and that induces positive charge to the one that is beside it. I think I want to call the second code now before I continue. The second attendance code. Get ready. I hope we are ready for that. So the second code is 7. UF9S. 7, figure 7. U for union, F for football, 9, figure 9, and S for sports. 7UF9S. The letters are in upper cases. 7UF9S. Thank you. I want to give you time to, I don't know why you keep posting the attendance code. It's not necessary. And I think Rachel, you have to stop it. You've been posting, and Taufik Barakat, you've been doing that. Please, you don't have to post this. Tolulope Shofuruwe, you don't send the code. You are not helping anybody by sending the code. I want to believe you have put in your code for today. The second code has just been shared, and I will just want to continue with the class. Give me a minute, please. I want to sort out something. Okay, so we can continue now. I want to remind you that dipole-induced dipole forces are weak forces, but because of the permanent dipoles that are present in one of the molecules, they are stronger than the London forces. So you remember in London forces, it's just non-polar molecules all through. Then dispersion forces and in dipole-induced dipole forces are generally referred to as van der Waals forces. So I've given another example there. When you have water and oxygen, you have dipole and induced dipole forces of interaction. And then if you have carbon dioxide in ethylene or xenon in water, then you will have this type of interaction. Then there is this other one that is stronger than the van der Waals forces, and that is the dipole-dipole attraction. And as I've put it here, from the name, those are molecules with permanent dipoles coming in close contact with another molecule of permanent dipoles. So dipole-dipole attractions are from permanent dipoles in the molecules that are coming together. So these forces are electrostatic forces between permanent dipole molecules, and they are oppositely charged ends. We attract or attract each other, simply put that way. So the part that is carrying a permanent negative charge, we attract the side that is carrying a positive charge that is permanent on the other molecules. So this is not about inducing charges or inducing dipole. For example, you have formaldehyde that is polar because of the presence of oxygen that is highly electronegative and bonded to carbon. So without any coming together with anything, they carry these dipoles permanently. And so based on the polarized carbon-oxygen bond, you're going to have dipole-dipole attraction between molecules of formaldehyde. And if you look at CH2Cl2, and you compare it with CF4, CH2Cl2 has permanent dipoles. CF4 is non-polar. And you will find that the boiling point of CH2Cl2 is higher than that of CF4. Although CF4 has a higher molar mass than CH2Cl2. Carbon is 12, hydrogen is 1. So you're going to have, chlorine is 7.5. So if you look at the summation, it's less than the molar mass of CF4 is actually larger, but we will find that CH2Cl2 is having higher boiling point because of the nature of the attraction between the molecules. Dipole-dipole attractions are stronger than than London forces that you will have in CF4, or non-polar rather in carbon. In carbon, you're going to have it as in CF4, you have a complete non-polar system, so you're going to have dispersion forces. And here you're going to find that when you have larger dipoles, you're also going to have stronger attraction. So the larger the dipole, the greater the dipole-dipole attraction. And dipole-dipole attraction forces, like I said, they are stronger than the van der Waals forces. That is, they are stronger than the first two that I mentioned. Now, you can also have ion dipole and ion-induced dipole. In this case, you have an ion. How do you form an ion? You form an ion through the loss or gain of an electron. So they are in a different class than those ones that have permanent dipoles. Because for those ones that have permanent dipoles, it's due to differences in their electronegativity. But the ones that are ions is because they have lost an electron or they have gained an electron. So when an ion comes in close contact with a molecule that has permanent dipole, that is a polar molecule, the kind of attraction that you have, or the attractive forces, is called ion dipole attraction or ion dipole attractive forces. If you have an ion that is coming in close contact with a non-polar molecule, then it's going to induce dipole on the non-polar molecule, and that is ion-induced dipole kind of attraction. So for ion dipole, you have force between an ion and a dipole. So we are talking about a full charge and a partial charge attracted to each other. And an example is seen in salts when it dissolves in water. The molecules in water, they have permanent dipoles. And that is the example that I've put in this diagram. If you look at this diagram, you can see that sodium ion is surrounded by water molecule. And because water has permanent dipole, the ion itself is carrying a positive charge, that is a positive ion or a cation. So you can see the kind of attraction is actually ion dipole forces. And for ion-induced dipole, these are forces of an ion or non-polar molecule. When they interact, you form dipole-induced dipole force. And so the charge of the ion will cause distortion of electron cloud on the non-polar molecule. So that is how it happens. And ion dipole interaction increases as the charge increases, and also increases with smaller size of an ion involved. So when you have a small size of ion that is involved, it is able to draw electron towards itself, such that you can see that the induced dipole will get to be very strong, and at the end of the day you have a stronger interaction. So they are stronger than the dipole-dipole forces. And also you can have examples in magnesium chloride and potassium chloride. If you consider these two, you will see that magnesium will have a +2 charge, and potassium we have a +1 charge, and the charge +2 is higher. So the ion dipole attraction will be greater in magnesium chloride when you dissolve it in water than when you dissolve KCl in water. And so you can do an exercise with the other one that I put there, considering KCl and CsCl. What do you need to consider here? Both KCl and cesium are in the same group. Chlorine that is common to both of them. So you need to consider their position in the periodic table. So before I close today, I must talk about hydrogen bonding, and that is the one I call the fifth type of attractive forces. And ideally, I should have thought this with dipole-dipole interaction, but because of its peculiarity, I said we usually pull it out, but I put it as the fifth, so we can spend, we can have a good number of slides and description of this kind of bonding. We call it hydrogen bonding, even though they are attractive forces. It's a special case of dipole-dipole, and it only occurs when you have a molecule that has H, that is hydrogen, covalently bonded to fluorine, to nitrogen, or oxygen. Just note those three. You must have fluorine, nitrogen, or oxygen because they have high electronegativity value. When they are involved in any molecule that has hydrogen that is covalently bonded, then you will have hydrogen bonding. Like I said, it's a type of dipole-dipole attraction, but it's peculiar. It's very strong, stronger than any kind of IMF. It's the strongest of them. So it's very unique. And because it's stronger, it's able to impact the physical properties of molecules more than any other type of attractive force. So the dipole-dipole interaction between these bonds, they are usually very strong. And example, I gave you HF. So for H, F, you're going to have hydrogen bonding. In water, the molecules are attracted by hydrogen bonding because hydrogen is covalently bonded to oxygen, and hydrogen is also covalently bonded to fluorine. So when you have molecules of HCHF, the kind of interaction between them, or the attractive force between them, is referred to as hydrogen bonding. Ditto the NH3, acetic acid, and acetone in water. And you can see the structure here where we have shown you clearly that there is always this hydrogen and oxygen coming in, having this attractive force in the entire structure of water here. If you trace it very well, you will see hydrogen and oxygen together. So what other thing do we need to know about hydrogen bonding? Is the reason water has its unusual property, though for a small molecule like water, molar mass is just 18. You don't expect it to have very high boiling point, but that is the case. And the reason is the hydrogen bonding. So if you compare it with H2F, H2F has molecular mass that is almost double that of H2O, but the boiling point of H2F is just minus 60. Whereas boiling point of water is 100 degrees Celsius. This is because H2O molecules experience hydrogen bonding while H2S molecules do not. And this strong attraction between water molecules require additional energy to separate the molecules in the condensed phase. So the boiling point is very high. So this is one of the reasons water is a very strong solvent. We refer to it as universal solvent and has high heat capacity and can expand while freezing. So that is going to be all for today. I would like to know if you have any question within the next 5 minutes, so I can take your questions. And if there is anything you are not clear about, you are free to say it. So while I'm waiting for your response, I would like to dictate the last code for today. I hope you are with me. So the last code for today is KVWYV. K for cola, V for Venus, W for water, Y for youth, V for volume. KVWYV, all in upper cases. Active blog Niger TV. I have warned you several times not to share the code. So, yes, somebody is asking me, how do we get the lecture slides? The lecture slides are available on this YouTube channel. You can watch again and again. You don't need any lecture slide. You can always come back here to watch, and at your own convenient time, you can write out the notes so you can have something to keep if the internet is failing you. Thank you. Yes, I don't know if anybody still has any question. At the end of the slides, I put some practice questions there for you to learn better on your own. Please do well to check the questions and practice them. Yeah, somebody is asking, is dipole-dipole force node part of van der Waals forces? I already told you I'm teaching 5 types of forces, and dipole-dipole is just one of them. Then I told you that dipole-dipole is not a type of van der Waals force. So I don't understand that question. Is dipole-dipole force nodes part of van der Waals forces? No. I taught you London forces, and I taught you dipole-induced dipole. And I said these two are the types we call van der Waals forces. So dipole-dipole attraction is not a type of van der Waals force. I think I've answered your question. How do we determine or identify these intermolecular forces now? It is simple. You must know the molecules. For example, I told you HCl has permanent dipole. It's a polar compound. All this is about foundation that you have in chemistry. HCl is a polar molecule because of the high electronegativity of chlorine. So when it's bonding with HCl, you have permanent dipoles there. So because you have permanent dipole, you know that it's a polar compound. And if it's coming in contact with any molecule, then you can determine the type of bond. For example, if HCl is coming in contact or is attracted to a non-polar molecule, that is a dipole-induced dipole type. If it is coming in contact with an ion, then it is ion dipole. That is how you know it. So I don't know if there's any other question. Is van der Waals forces also known as dipole-dipole attraction? I have answered that, and I think there shouldn't be any confusion in that. He said, how many dipoles are in H2O? It's not a question of how many dipoles. You know that water is a polar molecule, and that is why we say that its interaction is polar. And so when we refer to the type of attraction in water as a substance, it can only be dipole-dipole. But because of the uniqueness, it's not about how many, it's about the type. We are not talking about the number. Okay, if you want to know the number, then I can help you. Maybe what you are trying to know is if you can have more than one. Yes, you have more than one. Because there are electrons, there are also dipole forces of attraction. That is one. And because there is that dipole-dipole interaction that is unique, that we refer to as hydrogen bond, that is 2. So it's not 3. The general thing is that electrons are present in molecules, and that means you have London dispersion forces present in all substances. And in water now, you also have hydrogen bonding. So you will not say you have dipole-dipole attraction and then you also have hydrogen bonding in water. No, it is going to be 2, because hydrogen bonding is a type of dipole-dipole attractive force. I hope that is clear. How does the strength of a hydrogen bond compare to a typical covalent bond? And why does that matter in biological system? Time will not permit me to answer that question, but I've explained. Hydrogen bonding is the strongest. Thank you, and have a good day. I'll see you on Monday. That's cool. I've given the last code. I didn't turn off any. So.
And let me just shift it up stream. So what happens here? So that was announced at EMS one. That's not dating. Good morning. This morning, we want to continue from where we stopped.
Wednesday. But before we go on, AMS 103 will start in 30 minutes time. So prepare for that. So we start with pressure, temperature, and the RMS speed. As we earlier discussed, we mentioned the aspect of the importance of pressure in molecular motion. So we came out with this equation 22, if you can remember, where n small letter is the number of mole, your m capital remains your molar mass. So the RMS speed is the square of it. Like I said last meeting, that you can be asked to find the speed from this expression. So you have to remind yourself or be familiar with change of subject of formula in mathematics. So meaning that every one of you should be able to make V the subject of the formula from equation 22 before we continue. Because you will need the equation in the area of calculation and be able to apply it to solve simple problems. So we can now move on for today. Your V remains the RMS root mean square speed of the molecule, and V is the volume, the small v without RMS. And equally, you should be able to make T, the absolute temperature, the change of subject, by squaring both sides. The square root on the other side will go, and that gives you equation 23a. So take note of these three major points. Number one Roman figure is that the absolute temperature can be measured when the volume is also altered in measurement. But the principle observed in measurement is different from the principle observed in the ray calculation. So measurement takes into consideration constant values like R, capital R, which is always 8.31. But when it comes to the real aspect of theory, you ignore that because it's already in place in the means of calculation. So take note of that in the application of equation 33. Now, the average translational kinetic energy per molecule in an ideal gas gives you this expression. So it's as if we are putting two equations together in one. Sometimes you'll be asked to calculate the mass of the gas. Then it is required now from this expression that you will make m small letter in that expression the subject of the formula. Okay? And so at the same time, you can say K average is equivalent to 3/2 kT. Boltzmann constant remains the value that we give in any calculation, any exam or test. So you don't need to worry about that. All you need to do is to Boltzmann constant remains the value that. So it's left for you to make T the subject of the expression if you have to equate the other equation together, put the other equation together. So take note of that. If you have to put that equation, so take note of that. This is because K is equal to R over NA. Your NA is the Avogadro number, which is also a constant value that will be given. That's what is expressed in the equation 25. So these relations are important in solving related problems along the line of the gas formula. So take note of that. And like I told you on Wednesday, the basis of this aspect of physics is purely calculation. So you should be able to remind yourself of the past mathematics, even from the O level, when it comes to compound angle, application of linear relations, change of subject. These are simple mathematics that you will need here, and you cannot do without that. So another advantage I want to give you, if you didn't go through good schools in your secondary school days, you can use the money to share with others. Have your friend around you who can put you through. If you have difficulties along that line, then come to our general office. Like I said on Wednesday, people will attend to you in person. There's no problem about that. So we can now move to the mean free path. The mean free path. A typical molecule moves through the gas, changing both speed and direction absolutely as it collides elastically with other molecules. So this you need to know that the mean free path is simply the path the molecule takes before it can escape from the container. And this has to do with the heat exchange, which is otherwise known as thermal energy. Thermal energy. Very important for you to note. So between collision, the molecule moves in a straight line at constant speed. This random motion is best described as the mean free path. And the cell is represented with lambda. Lambda is a common symbol that is required for you to do that. So our lambda represents the average distance traversed by a molecule between collisions. So collision is important as the key word to be observed in this subtopic. When two or more molecules, or in other words, particles, comes together when it comes to the area of atmospheric physics, there's bound to be collision. So your rate of collision is determined by the speed and the area occupied by the particles or molecules. So these two factors is important for you to note. It can be a question for you that which of the following is important before an increase in collision can be made possible. So you pick one of the correct answer along the line. So mean free path varies inversely with the number of molecules per unit volume. Also, mean free path varies inversely with the density of molecules. The mean free path, you have to note the other two factors. The larger the number of molecules, then the more the rate of a collision. Then the larger the density of molecule, the smaller the mean free path. So these are the key words you have to note. And I promise you the slide will be available for you. Next point, the average distance traversed very inversely with the size of the molecules. And this is very important. The size of the molecule in ideal gas is assumed to be the same. But when it comes to real particle motion, it's not the same. And so we have to consider the path taken by the molecules in that respect. Also note that the larger the molecules, the smaller the mean free path. In other words, that's like an inverse proportion from your mathematical point of view. The mean free path also varies inversely as the square of the molecular diameter. And sometimes we can change the diameter to radius with the assumption that every student should know that your diameter is the same thing as 2r. D equals to 2r, where D is your diameter, r is the radius. So anybody cannot say radius will be D divided by 2. That is to be clear. So the expression for the mean free path becomes this: lambda equals 1 over square root of 2 pi d square n over v. And look at the limit of that square root. It is important to us in this aspect of the topic. So you may now be asked to make d or calculate d. So that means you have to make d the subject of the formula. So everybody can do that. Just say lambda over 1 cross multiply. Be able to come up with d, your cross multiplication, and make your direct substitution. Pi will be given to you in any question, either test or exam. The exam value for pi, either 22 over 7 or 3.142. So, and if it's not given, you should be able to substitute that because you have been using it from your secondary school days. Very important. So, this question has been given to you now to try and see how it works. What is the mean free path for oxygen molecules at temperature of 250 Kelvin and pressure of 2 atmosphere? Assume that the molecular diameter is that, and you also assume that the gas is ideal. The first thing to note in this aspect of the question, when the temperature is given in Kelvin, you may not worry. So, to remind you again, the AMS 103 will start as soon as I stop. So, be prepared for that. So, while you are trying this question before I show up the solution, I would like to dictate the attendance code. Now listen to the attendance code. A258A again. That is capital A258A. Okay. Yes, I can see your response. All right, back to the question. you have been given the temperature to be 250 K. I was saying that in some other aspect of the questions, if the temperature is given in degrees Celsius, you have to do the conversion to Kelvin because we are dealing with the ideal gas. Ideal gas considers the absolute temperature. So you must bring your temperature to a 273 Kelvin in addition. So the value 1 picometer is the same thing as 10 to the power minus 12 of a meter. You have to consider that before you make your substitution. And 1 atmosphere is something as 1.01 times 10 to the power 5 Pascal. That's the unit, or some other times can be Newton per meter square. It's the same thing. But you need that conversion and substitution before you can solve the problem. I'll now come back to the mean free path formula, 1 over root 2 pi d square n over v, which is equivalent to kt. K is your Boltzmann constant, root 2 pi d square p. Make your correct substitution in order. You can see the value you are going to get. Your Boltzmann constant is 1.38 times 10 to the power minus 23 multiplied by 250 Kelvin. Then root 2, the diameter is given already, 1.4 times 10 to the power minus 4. Then square that. The n over v is already given. By the time you make your calculation, then mind you, you have to be familiar with your own calculator. You don't borrow calculator only during the exam, because sometimes if you are not familiar with your own calculator, it gives you problem during any test or exam. So have your own calculator with you. Like I announced on Wednesday or Monday, if you find it difficult to get your own calculator, let us know that. We'll link you up with your local government chairman who can make such a provision. So that's the answer to that, 2.75 times 10 to the power minus 8 meter. The B part, assume the average speed of the molecule is 500 meters per second. What is the average time between successive collisions for any given molecules? For any given molecules. Now, while I am doing that, I want you to take down the second attendance code. And don't put your name or somebody's name where your C is not presently attending to this lecture. Because I learned that you have been doing that. Listen to the attendance code. 4HD, D capital, right? 4HD 3A, A capital 2. I repeat, 4HD 3A. Yes. Now back to the problem. T will, because T small letter now, which is the average time you have to calculate, that will be lambda over the V. P is your speed, lambda is the mean free path. Then substitute the value, and you have your answer as 0.22 times 10 to the power minus 19 seconds. These questions is to help you to see how it works when you are using your own personal calculator. Because up to now, I discovered in the normal class, some of you don't know how to convert the power of a unit. When you say minus 9 plus 5 as a power of a unit, you should be able to know what it is. Otherwise, in the option, you will still find your answer there. But that does not mean the answer you pick will be correct. So you have to remind yourself and be familiar with the conversion and calculation of power of a unit. That is to help you anyway. So the distribution of molecular speed, which is the final topic now. The root mean square speed gives us a general idea of molecular speed in a given temperature. Now, take note that we have ignored the issue of volume as in an ideal gas. We are dealing with temperature now. So the equation will change. So pressure, which is in relation with the initial volume, will be equal to 4 pi multiplying the ratio of m, which is your molar mass, over 2 pi RT. Pi remain the same, R remain the same, T represents your absolute temperature, everything to power 3 over 2. And that gives you your equation 28. Take note of this equation, is very, very important. M is capital here, is the molar mass of the gas, R is the gas constant, T is the temperature, and V is the molecular speed. The fraction of molecules with speed in an interval V1 to V2 now give you this expression. That is that fraction that has to be, can easily calculate that. That is integral from volume 1 to volume 2 for the pressure in relation to the change in volume. That's why you have P dV. And like I announced to you earlier, or told you earlier, you have to remind yourself of differentiation and integration in mathematics for you to be able to solve the problem in this topic. So in other words, we assume you have passed through secondary school before you come to this school. So integral here, you should know how it works. Integrate over V1 and over V2. And so the equation comes better. And the more you'll be able to solve the problem. Therefore, average speed for Maxwell's, the Maxwell equation, will be equal to the square root of 8RT over pi m. M remain your molar mass, R the gas constant, T is the temperature. That gives you equation 30. But sometimes you will only be asked to find the molar mass. It therefore means that you, as a student, should be able to make M capital in this expression 30, your change of subject. So if I want to make M, then square root both sides. V average, then that remove the square root of the other side. Then you cross multiply. Capital M now comes out, clear. You now have V average multiplied by pi M equals 8RT. Your M now becomes that 8RT divided by V pi, that V average. So substitute your value and you got your answer out. Equally, we can find this next slide. We can find the average of the square of the speed. That is V square of the average. That is equal to 3RT divided by M. That gives you equation 31. I've decided to number the equation so that it will be identified. So finally, your VRMS equals to root of 3RT over M. So the equation is becoming better and more familiar. That gives you equation 32. This will remind you that the more the equation you have, the more the opportunity to solve many problems. So you can be sure that in your test or exam, you have nothing less than 60% calculation. Others may be theoretical questions. And they are simple things. You are going to apply your expression. Next slide, which is like the final slide for you. The most probable speed, Vp, is the speed at which P, which is relevant to volume, is maximum. So VIP here is not the normal slogan, but this is the volume at constant pressure equals the square root of 2RT over M. What's the difference between the initial formula? The other one is 8RT. This one is now 2RT. So if you have to calculate the probable speed, it's different from the actual average speed. So you can only identify that with the formula. So with that, it is good to say you have more than enough, both for the test and for the exam. So all you need to sit up and sit down with the questions and the theory aspect of this topic. So I'm believing that you'll be able to do well. I will round up by giving you the last attendance codes. Yes. Ready? 48W53. 48W53. Okay? All right. Finally, on that, go and prepare very well for your test. There's nothing new except what you have just been taught. So if you have any problem before the test time, you have the right to contact the general office of the department where this course is being coordinated. So that will be solved by the. Thank you. There's no other question. So AMS 103 will start now. Get yourself ready. Thank you.
All right. Okay. All right. Good morning once again, everyone. Now the lecture it's here fully. And of course, I need to remind you, this is the MS 103 class, Introduction to Computing. Okay. Of course, I need to remind you, this is the MS 103 class. Now, today, the topic before us this morning is the role of information processing in society. Okay. The role of information processing in society. And at the end of this lecture, it's expected that you as a student should be able to explain the concept of information processing. All right. Then you should be able to distinguish between data, between the key concepts in this topic, and that is between data, information, and knowledge. And of course, you should be able to describe the information processing cycle, then identify the types of information processing. Then at the end of the lecture also, it's expected that you should be able to explain information processing systems and their components. Then you should discuss the role of information processing in society. And lastly, be able to identify the social, the ethical, and the security issues related to information processing. All right. Now let's quickly go to do a form of introduction, to the things we are doing. Now we know that information processing is the foundation of modern computing. It's at the heart of computing, and is the fundamental reasons why computer exists. Okay. At the simplest level, a computer is not an intelligent machine. All right. Rather, it's a tool designed to receive data. All right. And then computer process such data according to defined instructions. Then thereafter, it produces meaningful results. All right. So you can see that from the smartphone that we are holding in our hands to the banking system. So all of these digital systems, they rely on information processing. So that tells you the significance of information processing in the society. So because in everyday life, information processing is constantly taking place. Okay. And sometimes even without our awareness, that thing takes place. For example, I mentioned the issue of the smartphone the other time. Now, when you as a student, you use your mobile phone to check information results online, your information processing is taking place. When you use your phone to send a request, that's a form of input to a remote server. And the server will retrieve and processes the relevant data. And then what you have is your result that will be displayed, on the screen, and which can be regarded as an output. So in the banking system as well, and the same thing is similar, that when money is withdrawn from an ATM, for example, you understand, the system will process the account data, and of course, this time in real time, to verify the user's identity. Okay. Then you will check your account balance, update your records, and dispense cash within seconds. So all these processes, from the time you input your details and the time that your cash is dispensed, a lot of information processing, goes on along that time. So now this illustrates that information processing enables us, it brings speed, accuracy, and reliability in the modern system. So now, and of course, the information processing is useful in education, it's useful in banking, healthcare, and government, as we are going to be seeing later. And so it means that understanding this concept is very essential for computing, for data science, and information systems. All right. Now let's move on. Okay. I